Oh, the file. Airdrop the file. Oh. I had it set to only. Okay. Yes, now it's okay.
Start time.
Okay. Alright, so today we are introducing convolutions and the Fourier transform. We're gonna go over the definition first, and then the definition only covers the L1 case for F and G, so the proposition kind of covers for LP and LQ. And then we'll go over the general properties like commutativity, associativity, as well as introducing the Fourier transform. And then lastly, we're going to end with some applications for using the Fourier transform. So to start with the convolution, how we're defining it, we're going to use the star symbol as the operation for F and G in L1 in Rn. And that is the F star G of x is the integral of f of x minus y times g of y with respect to y. So some important preliminaries that we just wanted to kind of jog your brains a little on reminding what those are. We're going to use the number 2, 1, 10 a lot, and that is just that if f and x are measurable, you can add them, subtract them. That is supposed to be f times g, so we can multiply them, and those are also measurable. The finiteness principle, so if the integral of a function exists and is finite, then the function itself is finite. That was really important. 2 to 11 is just that absolute value inequality for integrals. And then the translation invariant, we can shift shift the function over. Holder's inequality for 1 over p plus 1 over q is 1. And then, of course, Tonelli and Fubini are going to be used, as well as from group A, the linear change of variables was really important for convolutions. And so just for why convolutions sort of make sense and are integrable, the big thing is because F and G are already in L1, or in that proposition when they're in LP and LQ, it's just a f times g with x minus y is just a composition of functions, and we're multiplying them. And so with that, and so we use the linear change of variables and that proposition to 110. F times g is going to be measurable. And then as far as the integral, we start because f times g is measurable, we take the integral of the r cross r over r cross r. And so because that integral is going to be less than infinity and makes sense, by Tonelli, we can split that up into two integrals. The integral of r over r of the integral over r of f times g. That is also going to be less than infinity and make sense. And so by the finite principle, the one integral is going to be less than infinity. So now Robin, or Ethan, I'm sorry. Like proposition.
Yeah. So we want to show that if f is an L1, g is an LP, then their convolution is also in LP. And also we want to show that the convolution of f and g is bounded by the product of terms. So if, this is where we're going to have, well, I guess this is fine. So if you take, yeah, this is confusing because we don't have the actual integrals, but Yeah, so there's actually supposed to be something else in front of this, which is we're bounding f star g of x, right? And so if we take the absolute value of that, we have that it's less than the inside absolute value, which would be oh, okay, this is done. Okay, so we have that the star of the absolute values of each function is going to be greater than the absolute value of the convolution. And so we have that this is equal to f to the 1 over p times f to the 1 over q, since 1 over p plus 1 over q is 1, star g, and then you take out and then you oh yes, and this is Holder's inequality with using a translation invariance. And then with this inequality, we can plug this in to see that f star of g, the p norm, from like, oh wait, you can't see the notes. Oh wait, you can. From the p norm is this, and then you plug this into here. And then this becomes the norm, the L1 norm to the p times the LP norm to the p, which is less than infinity.
Since L1, I mean, if you use the holder, and it's supposed to be the L1 times L infinity. Am I right?
That's the next case, I believe. Here we're less than infinity.
Yeah, so maybe
We're between 1 and we're not using 1 or infinity yet.
Yeah. Oh, I see. No. P is less than infinity and greater than 1.
We're not using 1 and infinity yet.
Yeah. So this is if P is strictly between 1 and infinity.
Oh yeah, that should really shake sense.
Sorry. Now this is now we're moving on to show that this function is actually bounded, and you can see that because this we already explained, and this we pulled the norm of g out of the integral. Remember this is actually an integral, this star operation. So you pull the norm of g out of the integral, and you get the infinity norm of g times the norm of x minus, like, there was an x minus y there, so. I don't know why it says dy. I think there was supposed to be an integral there. And this is equal to the norm of g infinity times the norm of f. Oh, yeah, I see. There's supposed to be an integral there. Yeah, so this is what we just showed for p equals 1 and q equals infinity. And then if 1 is less than p is less than infinity, you have the same argument as before, except now this time you have to use Holder's inequality instead of just pulling out g infinity. And this time you get norm of f, the p norm of f times the q norm of g.
check the time.
Oh,
You want to see what
yeah,
5 minutes. Okay, so I'll go through this really quick. So commutativity is basically just a two-parter proof. Use definition. You make a linear change of variables to sort of shuttle the x minus, variable of integration part over to g. Then you're just using the definition again to get f star g equals g star f. For associativity, it's a little longer. We're applying the definition twice. We get this integral here. We're able to absorb the f of x minus y into this integral over dz because it's a constant with regard to that variable. Here, because we have that the integral is finite, because the convolution itself is finite, we're able to use Fubini to exchange our variables of integration. We do another linear change of variables, and then we're able to reapply our definition again to get the desired associativity property. This immediately follows just from the integral being a linear functional. Here we're just able to pull out the constant. And then for distributivity, it's again just using the fact that the integral is linear and that the functions in the integral are assumed to be integrable. Now, this is the definition of the Fourier transform. Fourier transform is the convolution is going to be, or the Fourier transform of a L1 function is going to be bounded. Here's the proof. We just use our basic inequality from our of integrals here. The magnitude of the exponent is, or the exponential function is just 1. Function is assumed to be an L1, so we get that this function is bounded. For convolution, here we're just applying our definitions, and we get this integral. We are able to we are able to use Fubini here to interchange the order of the integrals. We also rewrite the integrand in this way so that we can get a Fourier transform of f. We're also using translation invariance here. And then we just use the definition of the Fourier transform again to get that the convolution of f and g is just equal to the products of their Fourier transforms.
Oh. Oh, okay. Yeah. We mentioned this more, but Fourier transforms are especially important, and convolutions are especially important in any kind of differential equation, including PDEs. Yeah, and convolutions are important because, especially in probability, it's encountered a lot because the probability distribution of the sum of two random variables is given by their convolution. And yeah, obviously you want the sum of two random variables like all the time. In number theory, the convolution comes when you're considering the Dirichlet product or convolution in analytic number theory. And that's kind of, you can see it defined there. But instead of like the integral domain being like R, here it's the divisors over, it's the divisors of M. Oh, this is supposed to be B, by the way. Like, this is supposed to be B. You can see how it looks like the normal convolution if that was B. Yeah, a lot of the results in analytic number theory have to do with this convolution in some way. So like the Toshin function, which is the number of divisors, the Mobius function and Dirichlet series all have important connections. And yeah. Also, it's good for diffie cube.
Okay. Group D.
Yeah, everything is fine.